So to kind of get you an idea of what you can do with optics.
Oh,
So,
no.
and then I'll pass this around as I give the lecture, but basically what this is that it's a mirror, and then you have another mirror on the bottom. So looking at it like, and you can kind of do this because it's pretty severe. So if you've got this mirror like this, okay, what you can do is, this is kind of a little weird, I'm just going to tell you. So what type of mirror is this, concave or convex?
Concave.
Concave, right? So with this one, there's a couple of things I want you to do with this. So bring it in really close, and it looks a little disturbing. Okay? I'm just telling you, but what you're going to see, and here's what's going to be important, is that when you bring it in really close, you're going to see an upright image. Okay? Then take it, begin to move it away, and then you're going to reach a point where it gets really, really blurry, and you can't see anything. But then, when you move it past that point, then you're going to see yourself, but then you're going to see yourself upside down. So one of the ways that you can always tell if it's a concave or convex mirror, if it's a concave mirror, okay, like this is, you're going to get two images. When you're up close, it's going to be upright, and then when you move further away, it's going to get flipped over. If it's a convex mirror, you will only see an upright image that's smaller, okay? So that's how you can always tell the difference. So that's one thing, you can do this. You can also do it with the one that has a hole in it, and that gets a little bit weird because it's like your head disappears, okay? I'll leave that up to you. But here's the cool thing that happens with this. No, don't eat the M&Ms, okay?
What?
Someone's gonna eat them.
I'm just telling you. So if you put those at the bottom, and then you put this back over the top, and if you look just right, what you'll see is that the M&Ms will appear to float right here on top of this opening, okay? And it gets a little weird, okay? Just because if you get this just right, it looks like you could just grab those and pick them up. So basically what's happening is that within the mirror itself is that the light's coming in, it's bouncing off, it's hitting this, and then you're recombining all of those images, okay, all of those photons into a virtual image of the M&M. So it's kind of like what I did when I had like the little screen, okay, that I put on top of the iPad, and it was projecting in all the directions, and we got this like virtual swimming fish or the heart or whatever we were looking at, okay? So it's kind of that same idea. So with this one, the light's coming in, it's bouncing off, it's bouncing up to the top, and then you're recombining these images in all directions so that it looks like some floating M&Ms, okay? All right, so I'll pass that around. Try not to get too flipped out over the deal. So,
It looks like flying saucer.
I don't know about that.
Okay.
Turn the light back on.
Yeah, don't eat the mirrors. M&M.
Oh my gosh, I can see one of them.
The M&M, that's what I'm
I see like one and a half. That's so weird.
What, are you trying to grab them or what?
I was just moving it around so I could see them.
Okay.
Do you see those?
Yeah, but they look huge, so.
Yeah, they look massive. Why can't I grab them? I don't know.
This is
Why
sorcery.
doesn't this
Cool.
magically
Second
rub a piece
semester,
of
we
M&Ms
start
into
doing
my
sorcery
hands?
in physics.
This is
Okay.
Oh,
The
yeah.
dark magic part.
You're a wizard,
I
Andrew.
don't know about that.
You're a wizard,
Okay.
Barry.
So,
You're a
for
wizard,
those of you
Tate.
that aren't focused on that, I'm going to go through this idea of a converging lens. Okay, so we're going to go through the math on this one, and we're going to see what's going to happen with this. So, here's the odd thing with converging lenses. You can actually, it's kind of like a concave mirror. You can produce two types of images. One that's on the other side of the lens, and one that's on this side of the lens, okay? So, in that, and one's inverted and the other one is upright. One's going to be real, the other one's going to be virtual. Okay, so with that said, so from yesterday, here's your heart and soul of this, okay? There's a couple of things. Here's this equation for magnification, and this is the one that I would recommend that you would use because that's going to allow you to figure out what's going to happen later on when you have, like, if you're trying to figure out is it upright or is it virtual. So, here's the deal. So, I've got an object that's 40 centimeters away. I got a focal length of 20 centimeters. I'm trying to figure out a whole bunch of different things. So here's the deal. Is my object distance going to be a positive or negative value?
Negative? Negative?
Object distances are always positive, okay? Object distances are always positive. So that, this case, that's going to be a positive 40 centimeters, okay? Now, we're going to get to the image distance in just a second. Now, my focal length. Is my focal length going to be a positive or negative number?
Positive?
Positive, why?
It's on the other side.
No,
Because it's going to be an inverted image?
nope.
Oh, okay.
Remember, if the lens or the mirror brings things together, that's a positive feeling, right?
Oh.
If it spreads them apart, that's a negative feeling, right? So this lens is taking these rays and it's bringing them together, okay? So since it's bringing them together, since this is a converging lens, AKA a
Positive. Convex.
convex lens, okay? That means it's going to be bringing these things together, and my focal length in this case is going to be a positive 20 centimeters. If this had been a concave lens like this, that light would have hit and would have spread out, and I would admit then my focal length would have been a negative value, okay?
So for mirrors, this is the opposite?
No. Well, okay, here's, don't get wrapped up in that.
Okay.
It is, but it isn't. So here's the bigger idea. Just look at what's going to happen with the rays. If you have a converging lens, it's going to be bringing it together, okay? But Ryan is right. If this had been a mirror, okay, then that light would have got scattered off of that, and then I would make that a negative 20 centimeters as my focal length, okay? So what you want to do is think through what is happening with the rays. Are they converging? Are they diverging? So if you have a converging lens that's being brought together, if that had been a mirror, it would have scattered it out and you would have had a negative focal length. Okay? Good with this. Okay. Now, once we get this, now we can do the math. So what I want to look at is that usually, like I said yesterday, 95% of the time, you're solving for the image distance, okay, with this thin lens equation. So you're going to have 1 over f minus 1 over so is going to equal 1 over psi. So in this case, I'm going to take 1 over my focal length, do 1 over 20, minus 1 over my object distance, which is 40, equals 1 over psi. So somebody take 1 over 20 minus 1 over 40, get an answer, and then take the inverse of that.
40,
What'd you get?
30,
Positive or negative?
positive.
40 centimeters. Okay. So what that means, okay, and let's talk about the significance of that positive sign on here. So my image distance is going to be twice as far away as that focal length is. So I've got a focal length here that's symmetrical, that's 20. I've got another one that's over here at 20. And then this is going to be out here at 40. So notice that this image distance is a positive value. In this situation, that positive value means that that image is in the same direction that the light is traveling. So if you look at what we did yesterday, when we had this, where's it at? When we did all this with this concave mirror, what we did yesterday, so here's all the calculations that we did yesterday. So with this one, my image distance was a negative 13.3 centimeters. So with that one, the light was coming in, it was hitting, it was bouncing off, but the image was in the opposite direction that that light was going. So on your image distance, if it's a positive value, it's in the direction that the light is going. If it's a negative value, it's in the opposite direction that the light is going. Okay? All right. So, let's talk about magnification. So now, when you're just looking at this, okay, if you're just looking at this, okay, here's going to be my image, right? I'm going to try and find that magnification, which is going to be my negative SI. So my image distance, we said, was, in this case, negative 40 centimeters. Well, it's 40, but there's a negative sign in front of it.
In front of the SI. That's
So-
the formula.
Oh, okay.
Oh.
Yeah. Okay. And then I've got my divided by my object distance, which was also 40. So I get a negative 1. So here's the deal. So if you get a negative magnification, that means that the image is going to be inverted. If you get a positive magnification, that means that image is going to be upright. Okay? So, so then you get into, well, is it a real or virtual image? It's a real image. My magnification is going to be negative 1. Is it upright or inverted? Nope, it's not upright. So, I got a negative magnification. It's inverted. So whatever size the object is going to be whatever size this is. Okay. Now, let's talk about what's going to happen to the magnification if I increase my object distance. So in other words, if I take this and I move it further and further out. So if I take that and move it further and further out, I'm not going to change my focal length, okay, because that's a fixed property of the lens. So if I made that, let's say instead of 40, let's say I made it out to 60, okay? So then so somebody did the math, take your calculator, take 1 over 20 minus 1 over 60, and then flip that over.
30.
So SI would be 30. Now if I look at my magnification, then I'm going to take 30 and divide it by 40, which is going to get me 0.75. So if I move that thing further and further and further out, my magnification is going to become smaller and smaller and smaller. Now, so you can look at the math side of it. You can also just look in terms of what happens with the ray optics. If I move this thing out here, then when I draw those lines, okay, then you can just kind of look at those lines and go, oh, right, where those meet is going to be a smaller and smaller and smaller value from that primary ray axis. You can just look at what's going to happen to the ray optics and go, oh, it's going to be a smaller value because of how the interaction of those lines and how those are going to play. Okay. Now, of all of them to try and actually see, this one you can make the math work. But this one here is extremely difficult to actually make happen. Mainly because you've got an object distance that's here. So you'd have to look at that, and then you're going to create this virtual image that's going to appear out here and kind of float. So that's what I was trying to kind of show you yesterday when we had like the floating 4. Okay? So that's kind of how this deal was going to play out. So if you do the math on this one, so my focal length is now 40. So here's the difference between these two. With this one, my object distance was outside my focal length. Okay? This one, my object is inside my focal length. Okay? So I've got the exact same numbers, but I've basically switched these up. So in this situation, it's easier to do the math, actually a little bit easier to get the math right, and then try and figure out, wow, how can that actually happen? So if you do the math, I've got my object distance, okay, is 20 centimeters, is that going to be positive or negative?
Positive.
Okay, that's going to be positive 20 centimeters because my object distance is always positive. What about my focal length? Positive or negative? Positive, because it is a converging lens. Don't flip out and go, well, but yeah, but it's going to be over here. It doesn't make any difference, okay? It doesn't make any difference where that image shows up. As long as you have that value, okay, as long as you know that it's a converging lens or a diverging lens or whatever that is, doesn't make any difference where the images are going to be, okay? Doesn't change anything. So now, I've still got a focal length that's now going to be 40 centimeters, okay? And now I want to figure out my image. So in this situation, I'm kind of running out of room, so we're going to work this down here. So now I've got 1 over my focal length, which is going to be 1 over 40, minus 1 over 20 is going to equal 1 over psi. So somebody take 1 over 40 minus 1 over 20 and get me 1 over psi. What do you get?
Negative 40.
Negative 40 centimeters. Okay. Now, here's the significance of this. Notice that I've got a negative value here for this image, and this is where this provides a nice contrast. So over here, my image distance is a positive 40 because it was being formed in the same direction that that light was traveling. With this one, I've got a negative SI because the light is going in this direction, okay? But what I'm actually seeing is the image that's back there. So the optics on this gets a little bit weird because what's happening is that light wants to travel in this direction. But what's happening is that part of that light is getting reflected and refracted back to here. So that it isn't like it's a mirror where all of that light goes through or it gets bounced off. Only part of that light is going to get refracted back and form this image back here. This is why this is so hard to see, because this one's easy to see because all of that light is going in this direction. Oh, it's going to create this really, really bright image. It's easy to see. Wow, we have an eyeball. Cool, right? And thank God this isn't how our eyeball works. Because if this is how our eyeball worked, where would we have to put our optic nerve?
Outside.
Yes, we'd have to put our optic nerve out here, okay? Which would get in the way of the image to begin with, okay? Yeah, it's like, huh?
I'm so confused.
About what?
Everything.
Everything.
Everything?
You need to
Okay.
back up version.
Once we start doing some labs, this will make sense,
Okay.
okay?
What's the difference?
Light acts too weird.
Huh?
Light acts too weird.
Oh, light does, it
No,
does,
it's
it
the
does
mirrors,
that.
not the light.
Okay.
Mirrors are done.
So now, let's talk about our magnification. So I've got a magnification
Virtual.
that's going to be my negative of a negative 40
So,
divided
one.
by my SO, which was 20. So my magnification is 2. So now, notice my magnification is a positive value. So since I have a positive value for my magnification, that means the image is
Upright.
upright and it is twice as big. Okay? So this light's coming in here, it's kind of coming through. So this is, notice here, this is where I'm using these dashed lines, okay? Like I did yesterday with that convex mirror. So the light is traveling this way. What the dashed lines are showing is the light that's going in the opposite direction. So if your eyeball was here, this is what you would be picking up. Okay? So you would have to have your eyeball here to see these rays coming back towards you. It's a little weird, but just stay with it. Now the good news is that it magnifies your image. So if this was our eyeball, the advantage of it is that, or disadvantage, is that everything would look twice as big. Okay? So that'd be kind of weird.
So like it looks for me and Liza.
Yeah. Okay. Fine. Don't ask me. Okay. So is it upright? Yes. Do you think that's a real or virtual image?
Virtual.
Virtual. There's no way on God's green earth that you could actually project that onto a screen. okay?
Oh.
Why though?
Huh?
Why not?
Because physically, if you were to put like, I keep forgetting I can't scroll with that. Because physically, if you were to put a screen here, it would block the light source itself from getting there. Okay? Unless this was like, even if it was emanating the light, as this would come through, this light is getting refracted back. So this would be something like you would see with your M&Ms. Okay? Because this is being created by part of that light that's getting refracted back to this point. So you could see it, but when you went to touch it, you couldn't. Okay? So you couldn't put this onto a screen. Whereas this one, because it's going in the direction of that light, okay, this I could project onto a screen, which is why your eyeball looks like it does. So your screen is your, okay, anatomy and physiology people. Where does the image fall in the back of your eye? Is it
We haven't covered that yet.
Pretty sure it's the retina. Yes.
retina? Yeah, let's go with retina. I don't like biology, but anyway, it's a little weird.
No,
Okay.
it's biology.
Now,
You look so-
this one, this one is tough to figure out conceptually. This is the one that you will see most often, mainly because it's the most real-world application. Oh, hey, here's your eyeball. This is how it works. You're forming an image. Here you go. This one, that gets a little bit weird, but sometimes it's there. All right, now we have a diverging lens. So right away, let's start with the focal length. Is my focal length going to be a positive or negative value?
Negative.
Negative. So right away, my focal length is going to be a negative 40 centimeters because of the fact that this thing is a diverging lens. Okay? So what's going to happen here is that I've got my SO, so my object distance is 20 centimeters. Even though it's a diverging lens, is my object distance still going to be a positive value? Yes, because your SOs are always positive, so that's 20 centimeters. So I've got my focal length, I've got my SO. So now, if you go through and do the math, so I'm going to take 1 over my focal length minus 1 over SO is going to equal 1 over psi. So in this case, I'm going to take 1 over a negative 40 minus 1 over 20. And if you do this math, you should get negative 13.3 centimeters. Okay. Now, again, here's what's happening here. So, the significance of this negative sign is this. As this light is coming in, all right, sitting this point, the light's traveling in this direction. Okay, so that's the main direction that the energy is flowing. But what you're forming is an image that's in the opposite direction of that light. So this is why I've got a negative value here for this image distance.
So if it's forming in the opposite direction, then it can't, then it's virtual.
For the most part.
There's always got to be an exception, right?
Okay? Just hold on. Just hold on.
Oh, for the
No. This is
You
kind of
haven't
important that
seen
we
dumb
figured this out as a civilization, or you wouldn't be wearing
I
glasses.
haven't seen that,
Okay.
but I just.
Hold on.
This is confusing.
And it's funny, what you will see with optics is just exactly what is happening right now. More so than any other topic that you will study in this class. Optics only plays out one of two ways. Either you really, really like it, or you hate it with a passion, okay? It's rare that people are indifferent to it, okay? Some people are just like, hey, it's okay. But literally, and this is no pun intended, if there's any polarizing topic that occurs within this class, it's optics. Literally, okay, acceleration, hey, acceleration is acceleration. Optics, literally, you go, this is horrible, okay? And I never want to study this again. Or you go, wow, this is kind of cool. I kind of like how this deal plays out. And literally, like I said, So,
I want to learn.
I will
I
strive
just-
to be
I can't.
Yeah, I don't get it.
We're all going to
Lines
try
on
to
the-
be
Okay.
in different.
Lines are drawn, the thing does the thing, and boom, I don't know how.
Lines are drawn in the
Fancy
sand
looking.
here.
lines are drawn and boom, here you go.
I don't like sand, it's coarse and rough and
All right.
But
It's
sand
guys
is
that
what
find
makes
stuff and I'm like, how
glass,
did you
which
figure
is
that
used
out?
for lenses and mirrors.
I know I'm making a bad joke.
I put silver
Trust
in your hand.
Hey, I will get you there, okay?
Well, that
Trust
makes it better.
I do.
Okay,
Passing a kid's stone.
so let's talk about the magnification, right? So my magnification is that negative psi over so, okay?
Sisal.
So I've got, in this case, negative of a negative 13.3 divided by my object distance, which was 20. And so you do this math, you get 0.67. So I've got a positive magnification, right? Got a positive magnification, which means the image is going to be upright. So we got that covered, okay? It's less, so I got 0.67, it's less than 1. So the object is going to be smaller. So if if my object height is 2 centimeters, what would be my image height? What would I do?
Multiply.
Yeah, just multiply 0.67 by 2. In this case, you get like 1.3.
4.
Yeah, something like that. About 1 1/3 centimeters, which bears that out, which is why this image is smaller than this one. So again, what you would do to get this, you're going to draw one ray that's parallel with it, okay? It's going to hit this line, it's going to go out, but with this one, it's going to try and work itself back to that focal length that's back there. So this comes in parallel, goes out, but it in effect is trying to go back to this point. So you've got this one. Then you've got one that's coming in like this, it's going to hit this, and it's basically going to reflect back on itself. So that's where you're going to get that second one that comes in here like this, and then you've got another one that comes in here, hits this, and then it's going to go parallel with that line, and then it's going to come back to here. So that's why I said, ideally you would always draw 3 lines to figure out where that object is, okay, where that image is, but certainly at least draw 2. Ideally, you would draw 3 to try and figure that out. Now, so part of your assignment today is going to be drawing these images. So today, it's going to take some patience, okay? It's going to take a scale. It's going to take these ray diagrams to try and figure out where this is. Yes?
So we're drawing the image based off the calculations?
No, no, no. Ideally, okay, in the spirit of, we'll talk about it on the assignment, but in the spirit of the assignment, you'd actually draw and figure out where it is based upon just the geometry part of it and the measurements.
Oh, I see why people hate this.
Yeah. And then you can do the math to figure out, hey, did I get kind of what I should get? Okay? So the problem is, especially if you try and draw this real small, it's going to be a train wreck. Because of the fact that depending upon your scale, if you're off by just a little bit and you've drawn this real small, then you're going to be off by a lot when you translate it back into distances. So when you're drawing these ray diagrams, okay, and you've got some to do on the assignment today, go big when you draw these. Okay, and I'm not saying take up an entire page, all right? But I'm just telling you, don't try and draw these tiny little ray diagrams or you're just going to get frustrated. And then I'm going to get frustrated. So whenever you're drawing ray diagrams, there's a minimum of 3 things that you always want to label. You always want to label where the object is, okay, where the image is, and then your focal points, okay? So those are the minimum 3 those are the 3 that you want to put on there. Because here's my problem. If I go to grade this and all I see is 2 arrows and nothing's been labeled, I don't know what is what. I don't know, is this your object or is that your object? So make sure when you're drawing these ray diagrams that you clearly label the focal points, the object, the image. And typically when you draw the lenses, you usually draw this as like a center axis, and you go, oh, everything's going to hit this center axis and go off. That's why this is showing up like this. Okay?
Yes.
Cool with that? Okay. All right.
How long is the assignment?
It's actually not all that
Okay, so
long.
what I'm telling
Always say
the
that.
in the case of going through, the top line will always hit the second foci on the other side, and the bottom line will always hit the first foci on this on the same side of the image as the object if it goes through.
Yes.
Yes. Okay.
Oh.
Can SO ever be negatives?
Huh? SO? SO, the object distance is never negative.
Okay.
Your image
I was
distance
trying
can
to
be
remember
negative.
what that was.
Okay. So here's what we have. Yes, ma'am.
So we don't need to end up converting everything to meters to do any of these equations whatsoever.
No, you can leave them all as centimeters as long as they're all in the same units.
Okay.
Okay?
Okay.
Yeah, I suggest you leave them in centimeters because it's the same ratio anyway. Okay, so these are the last two that we have left. Okay? And this is why you get two different images when you have concave mirrors. Okay? So this is the last one that we've got. So in this situation, I've got an object height of 2 centimeters. I've got a focal length of 20 centimeters. So let's start with focal length. Is that focal length going to be a positive or negative value?
Positive.
Positive. Because of the fact that this mirror is trying to converge these points back to this center. So when you have a concave mirror, your focal length is always going to be a positive value. So my focal length here is going to be a positive 20 centimeters. Now, my object distance is 40. So what's important here is that my object that I'm looking at is outside the focal length. Okay? So I'm out here, right? My focal length is here. So for those of you that still have, if you have a concave mirror, okay? So what's happening here is that I've got this outside of that focal length, which means that when I look at myself, it's easy to see with that big one. Where's the big one at? Okay? Just hold it back there, Liza. So take the bottom part and hold that up. No, towards you. I'll hold it out in front of you like this. Okay? What do you see?
I'm upside down.
You're upside down. Okay? So she is outside the focal length of that mirror, so she's going to be upside down. Thank you, Jerry. Now, when you bring it up close, though, and you're inside the focal length, then you
I
are,
was terrified.
you're what?
Terrified, but I'll
Okay.
right side up.
Beyond that,
Right side up.
right side up.